Christoph Yao Gadesa. I hold MPhils in mathematics education. I'll take you through Math 101, Algebra and Trigonometry. We are on Unit 3, which is Operations on Matrices, and we will start with Section 1, which is Matrix. Let's look at the objectives of Section 1. By the end of the section, you should be able to 1. Describe a matrix by indicating the number of columns and rows it has. 2. Give examples of special matrices. Let's consider some definitions. A matrix usually has M rows and N columns enclosed in parentheses. The numbers in the parentheses are called the elements of the matrix. Horizontally, there are rows, and vertically, there are columns. So to mention the matrix, we start with the row and then we follow it up with the columns. So here is example 1. We talk about a matrix that is 2 by 3. 2 by 3 here means that the rows are 2 and the columns are 3. So you look at the matrix and you see that row 1 is made up of 2, 3, and 1. Row 2 is made up of 5, 7, and 4. Column 1 is 2, 5. Column 2 is 3, 7. And column 3 is 1, 4. The matrix has 6 entries or elements. In general, an M by N matrix has M rows and N columns. Here is a matrix of size 3 by 3. The entries 2, 1, and 4 lie on the main diagonal of the matrix. The other diagonal is a skew diagonal. So there are 2 diagonals when it comes to every matrix. The main diagonal is 2, 1, 4. Then the other diagonal, which is made up of 7, 1, 5, is what we call the skew diagonal. There could be many rows and many columns in a given matrix. So a general representation of a matrix, say A, is what you are seeing there, which is A1, 1, A1, A13 up to A1n. A1n because all the ones we have mentioned so far are in row 1. So you will see that they start with 1. Each of them starts with 1. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and so on. Then the second one is A21, A22, A23 up to A2n. So that tells you that we are talking about row 2. And so the first entries are always 2. Then you can also talk about the columns. The first column is A11, then the second one is A21, and the third one is A31. You see that the second entry is always 1. So that tells you that you are talking about column 1. When you go to the second one, you see that the second entry is always 2. So A12, A22, A23. So that tells you that we are talking about column 2 and so on. So the first, when you take a particular entry, the first index talks about the row, the second one talks about the column. So if you take A23, that tells you that that element is in row 2, column 3. If you take A54, means that the element is in row 5, column 4. So an example, A12, that means that you have the element in row 1, column 2 of matrix A. Let's talk about some special matrices. The first one we'll talk about is the unit matrix. It is also called the identity matrix. It is a square matrix whose only non-zero elements are on the diagonal and are equal to 1. So you see that the main diagonal for that matrix is 1, 1, 1. All other entries are 0, 0. That is for a 3 by 3. You can also have a 4 by 4 unit matrix where the first row will be 1, 0, 0, 0. The second row will be 0, 1, 0, 0. The third one will be 0, 0, 1, 0. And the fourth one will be 0, 0, 0, 1. Another special matrix to be considered is the zero matrix. And for the zero matrix, each element in the parenthesis is equal to 0. You can have it for 3 by 3, you can have 2 by 2, you can even have 4 by 4. For a 2 by 2, the first row will be 0, 0, the second row will be 0, 0. For a 3 by 3, the first row will be 0, 0, the second will be 0, 0, 0, and the third will be 0, 0, 0. For a 4 by 4, the first row will be 0, 0, 0, 0. Second row 0, 0, 0, 0. Third row 0, 0, 0, 0. And the fourth row 0, 0, 0, 0. So that is the zero matrix. We can also talk about the column matrix. And the column matrix such that you have only one column, but there are three. You can also have one that there are 2 rows, or one that there are 4 rows, but one column. So if you look at the example here, matrix B is equal to 7, 3, 2. So this is where you have one column, but you have 3 rows. You can also have another one where the rows are say 2, but the column is 1. You can also have another one where the rows are 4, but the column is still 1. Just as we have the column matrix, we also have a row matrix. And in the row matrix, there is only one row. It is only the column that varies. So for example, matrix C is equal to 3, 1, 9. In this example, we have one row, but 3 columns. You can also have a situation where the row is 1, the columns are 2. You can have another one where the row is still 1, but the columns are 4. Another special matrix we can look at is the diagonal matrix. And the diagonal matrix is such that the main diagonal has non-zero element, whilst the rest of the entries are 0. For example, if you look at the matrix D, the main diagonal is made up of 21, 9, and -3, but the rest of the numbers are 0. The next thing to look at is what we call matrix equality. For matrix equality, 2 matrices are equal if they have the same size and if their corresponding elements are identical. So A is equal to B if and only if Aij is equal to Bij. For I is equal to 1 up to M, and J is equal to 1 up to N. So what this means is that for any 2 matrices to be equal, the order of the 2 matrices must first of all be the same, and then the number of elements must be the same, and then the type of element, the kind of elements must also be the same. So if you have a set A, which is 1, 2, 3, 4, that is 2 by 2. 1 first row, 3, 4 second row. And then B must also be first row 1, 2, 3, 4, 2 by 2. For you to conclude that matrix A is equal to matrix B. Let's find the transpose of a matrix. The transpose of a matrix is obtained by interchanging 8 rows and 8 columns. This means that if you have, for example, a 3 by 3 matrix and you want to find its transpose, the first row of the matrix becomes the first column. The second row of that matrix becomes the second column. And the third row becomes the third column. Let's consider the matrix A, which is A11, A1, A13 up to A1n, and the rest of them. At the next stage, we'll find the transpose of this matrix. The transpose of the matrix given previously is presented here. So you see a superscript T that indicates the transcript of A, and you see that row 1 in that matrix has become column 1 in this matrix. Row 2 of that matrix has become column 2 of this matrix, and so on. Let's look at the example. Find the transpose of the matrix M is equal to 2, 9, 7, 3, 1, 8, 5, 7, 4. Can you quickly work this and get your answer down before we get to the solution, so you can see whether you are getting it or not? Here is the solution to the previous question. I guess you've gotten it right. You see that row 1 of the matrix, which was 9, 7, has now become column 1 of this new matrix, 2, 9, 7. And row 2, which was 3, 1, 8, has now become column 2, 3, 1, 8. And row 3, which was 5, 7, 4, is now column 1, is now column 3, which is 5, 7, 4. Now, the matrix transpose satisfies some rules. Rule 1. If you find the transpose of a matrix and then you find the transpose of the answer, you come back to the original matrix. 2. If you add two matrices that are of the same dimension and you find the transpose of the answer, it is going to be the same as finding the transpose of each of them separately and then adding them. The same thing happens with multiplication. You multiply the two matrices, you find the transpose. It's the same as doing the transpose of each of them before multiplying. And remember, the two matrices must have compatible dimensions.